Okay, so we're going to continue on here in, this chapter. I want to say 19, hopefully. Could be wrong. Maybe it's 18. We are talking about, last time we talked a little bit about transition metals. We went over sort of some stuff that you maybe were aware of before. We talked about electron configuration with transition metals. We talked about some general trends in ionization energy. Really, the purpose for this is what we're going to talk about here for the rest of this sort of chapter really is complex ions. And complex ions, at the heart of those guys are metals. And a lot of time those metals are transition metals that are in the middle there. And we have some type of ligand that's attached, or multiple ligands that are attached to these guys that make a complex ion, kind of like what we did this morning with the copper 2 plus the NH3, which is a good ligand, making our Cu NH3 to the 4th here. The +2 charge. So this obviously is a complex ion, which is covered by Kf that we talked about in chapter 16, I think, which is the equilibrium expression. Once again, here, the ammonia is a good ligand because if you draw ammonia, it has those non-bonding electrons, which can donate them over to our transition metal that's deficient there in electrons as well. What you will also see is, again, the Kf is usually a very large number, as we talked about in that chapter. And that means that, in this particular experiment we just did, pretty much all of that copper is going to get kind of gobbled up there into the complex ion. That means when you do solve for the copper concentration of the ion at equilibrium that's free, it should be a relatively small number at that point, because the formation of the complex ion is definitely sort of favored in that reaction, as you saw with your beaker turning a very pretty color of dark blue. It should have when you hit it with the ammonia. All right, so let us continue on then and talk about coordination compounds and sort of what those guys are. So a coordination compound is really a sort of balanced charge compound. It consists of a complex ion and a counter ion. So you can really think of it kind of like an ionic compound. So there's like a positive guy and a negative guy. And when they come together, they equal 0. So just like it would do in an ionic compound, you want to make sure that all the positive guys and all the negative guys sort of balance each other out. So in this particular case, there's a couple of combinations that could happen to form a coordination compound. You can have a counter ion that is positively charged that would go with a complex ion that is negatively charged. So again, here the counter ion would balance out the negative charge of your complex ion. And vice versa, you could have a counter ion that is negative to balance out the positive charge of your complex ion. So counter ion, complex ions, they could either be positive or negative. Really, the counter ion is just kind of there to balance out the charge to get us to 0. As we talked about, a complex ion is a ion where in the center we do have a metal ion. Again, a lot of times it is a sort of transition metal with a large sort of positive charge. So here it's the cobalt, which is the metal in the middle, and it's bonded to one or more molecules or ions. These guys are ligands, which are, once again, Lewis bases. And as we talked about last time, Lewis bases are guys that can donate a pair of electrons to something like this. So in this case, the NH3 here all the way around, each of these guys would be ligands, along with the Cl here, which is Cl minus, would also be ligands, all the way around this guy here. Again, in order for something to sort of be a good Lewis base, it does have to have sort of a pair of unpaired, I'm going to say that right, maybe. A pair of electrons, let's go with that. It should have an unshared pair of electrons, or some valence electrons there. And again, things that are polar that have those non-bonding electrons are usually good. So like what we see here in water, we also see here in ammonia. And then also things that are negatively charged, again, in order to become negatively charged, you have to gain some electrons to do that. So those guys are also relatively good Lewis bases. Any questions on that there? Now, a thing that we touched upon in an earlier chapter when we were talking about KF is the idea of what is known as coordination number. And the coordination number is the number of atoms that are directly bound to the center metal. So when we look at that in the previous example here on the previous page, in each of these cases, the connection is really happening only through one atom. It is the nitrogen in each of the NH3s here that are going to be attaching directly to the copper or cobalt. And it is the chlorine, obviously, that will be attaching. So if we just add up, that's 1, 2, 3, 4, 5, and 6 atoms that are directly bound to the metal in the middle, which means the coordination number there would be 6 for this particular guy. Here would be the coordination number would be 6 in that particular case. To clarify and just to make sure, what we were talking about here is it's not 6 because there's 6 different things or molecules there. It is 6 because there are 4 nitrogens that are directly attached and there are 2 chlorines that are directly attached to it. So it's not always going to be, again, the number of ligands that are present. It has to do with the type of ligand that is present. And I think we also touched upon this in that chapter as well. But there are certain ligands, like the ones we saw on the previous page there, like water, ammonia, chloride, which are referred to as being monodentate, or some books call it unidentate. But they basically only bond in one atom per molecule. So in the case of the NH3, it's just the nitrogen that's attaching. In the case of water, it's just the oxygen that's attaching. And obviously in the case of chloride, it's just the chlorine that's attaching. There are certain ligands that can attach in multiple places, and ethyl endyl diamine, that's a mouthful, is an example of that. It is abbreviated a lot of times with just the simple EN designation. So if you see an EN in a formula, it's used a lot, and in an actual name as well, it's used as well. So they'll use that abbreviation in both places. You know, it looks something like this. If my organicness, if I remember some of that, looks like that move right there. And these guys should probably have a couple H's there. So this is ethyl endyl diamine. And when it does have, once again, a metal that's going to attach, in one molecule of it, we're going to get an attachment actually in 2 different locations. And they're going to be the nitrogen that has the non-bonding electrons. So it's going to be able to attach there and also here, which essentially gives you like a 2-for-1 deal on that deal. You get 2 bonding for every molecule of that, which is why it's bidentate, again, bonds in 2 places at once. So that's a very common bidentate one that occurs a lot. The other kind of common one that occurs a lot is oxalate. And that's oxalate, which is C2O4 2-. And if you draw oxalate, which, you know, roughly looks like this, perhaps. It is those single bonded oxygens that actually carry the negative charge. And once again here, if it went to attach to a metal, it is going to be those single bonded oxygens, 1 on each end there, that will be able to make that connection to the metal. So once again here, you get kind of a 2-for-1 connection in here. So if we had something like the coordination number here would be, so the coordination number here would actually be 4. So each of these EN molecules could attach in 2 places, and there's 2 of them, which means we have basically 4 attachments that are happening here. So this is what I was saying earlier. It's not always this number here is the coordination number. It is if it's a monodentate ligand, but if it's a bidentate, then obviously you need to adjust it based on how many are binding there. Any questions on that there? There's some that are polydentate, which means, heck, they bind in a lot of places. That's EDTA. That is like a 6 per molecule binding for EDTA. So it pretty much just grabs onto the metal really thoroughly there in 6 different locations on one of those molecules. That's why, as we'll see, EDTA is what is sometimes referred to as a chelating agent because it can pretty much gobble up metals and kind of tie it up really, really well as if it is used for that purpose. Now, how do we know how many ligands typically will sort of attach to a metal? You know, there's sort of very common sort of coordination numbers that occur, and it is sort of based on charge. So we can see here our guys with like a +1 charge, 2s and 4s. So, you know, a lot of times 2 things will attach in terms of that. If you get to like a +2 charge, 4 and 6 are very common sort of oxidation or coordination numbers. If you get the 3, 6 is also a very common sort of coordination number that occurs, except for gold. Gold will usually hang out with just 4 things sort of attached in that particular case. Again, the sort of larger the positive charge, right, the more electron deficient it is, right? Which means it's going to be able to maybe accept more ligands being attached to it than something with a smaller positive charge is not as electron deficient. Any questions on that there? So, hey, I drew it right. What do you know? That is our ED, that's our EN over here. And again, it's going to be binding at the nitrogen. As you can see, this is why I did not attempt to draw EDTA. That is the big thing right there. And it attaches in 1 place, 2 places, 3 places, 4 places, 5 places, and 6 places per molecule. And like I said before, bidentate, polydentate guys, like these guys are referred to as chelating agents because they pretty much trap metals really well. If you look at a lot of ingredients labels on lots of things like shampoos and other things like that, you'll oftentimes see EDTA listed in like the ingredients label. And again, it's used to kind of trap out metals and stuff like that to make sure nothing kind of gets in there. Here's a table, and you have a similar table, I think, in your book as well, of some common ligands. And again, water, ammonia, cyanide, nitrite, thiocyanates, hydroxide, and all the halogens are very common monodentate ones. Here's our 2 that we talked about there in terms of our bidentate ones, oxalate and ethylenediamine. This is diene, which is actually like ethylenediamine, but it has 1 more there. So it could attach actually in 1, 2, and 3 places, each at the nitrogens there. And on the bottom there is our ethylenediamine tetraacetic acid, which is EDTA. There's the bonus word for the next exam. Spell that. All right. I'm kidding, by the way. You don't need to spell. Or maybe I'm not kidding. Who knows? All right. So for each of these guys here, these are some complex ions and some coordination complex ions and some counter ions there. By the way, one of the common ways that coordination compounds are written is the guy in bracket is usually your complex ion. And then obviously the guy that's outside the bracket is usually your counter ion. So why don't you take a second and figure out the oxidation number of the metal that's in the complex ion. I want you to also figure out what is the coordination number for each of those guys as well. Okay, let's take a look. So if we take a look at this first coordination compound, something like this. So once again, what we do see here is this guy's in brackets, which means this is going to be our complex ion. This guy is outside of it, which means it is our counter ion. And coordination compounds, much like ionic compounds, do follow kind of the same rule. An ionic compound, the one that is positive always comes first, right? Followed by the negative. And the same thing happens here. So this tells us just by the order of everything, my counter ion here is positive. My complex ion overall is negative to balance it out. Well, we can start with what we got inside the complex ion. We have hydroxide, which overall is a -1 charge, right? And there's 4 of them. That gives me a -4 charge overall. Going to my counter ion, that is potassium, which is group 1, which means it should have a +1 charge. And since there is no overall charge in the coordination compound here, that means that our gold here will be taking on a +3 oxidation state for our gold. Question on that one there. Coordination number here would be? It would be 4. Again, this is hydroxide. It's 4 hydroxides basically attached to a gold. And hydroxide is a monodentate, so the coordination number here would be 4. Any questions on any of those guys there? Looking at our second one here, we see CrNH36 NO3 Once again, the guy in the bracket there is going to be our complex ion, and it comes first, which means it should be positively charged. And this guy here then would be our counter ion. That is going to be negative in this case. Charge on NH3 is 0. Yeah, not NH4 plus. This is NH3, so that is 0. NO3 is nitrate, which is -1 each, and there's 3 of them, gives you a -3. That means to balance out everything here, our chromium is carrying a +3 charge as well here. Any questions on that one? Coordination number here would be 6. Yep. NH3 is monodentate, and there are 6 of them. So the nitrogen in each of the NH3s are the one that is binding into the metal. Question on how to assign oxidation numbers. Now, if we look at our just complex ion in both of these parts here, what would be the overall charge on just the complex ion part for this guy? It is going to be -1. Yeah. Again, this is +3, -1. There's 4 of them. Gives you a -1 overcharge. That is why when we look at our counter ion, we just needed 1 potassium to balance it out, because ultimately we are taking +1 and -1 and putting it together. On the left-hand side here, or right-hand side, this complex ion, if we just took that part of it, would carry what type of charge? +3 charge would be good. Yes, it does carry a +3 charge. Once again, the ammonia is 0. This is a +3. So the overall charge on the complex ion is going to be +3. And that is why we have not 1 of these nitrates, but we got 3 of them there, right? To give us a -3 to balance it out as our counter ion. So coordination compounds are very much like ionic compounds that you do want to kind of equal 0. And you kind of use the counter ion to put the right amount of those guys to get the overall charge to 0. Any questions on any of that there? So let us talk about naming these guys, because everybody loves naming, right? The cation is always named before the anion. So just like ionic compounds, the positive guy comes first, and then the negative guy, both in formula and in naming. Within a complex ion, the ligands are named first in alphabetical order, and the metal is always named last. So in the complex ion part of the name, you should always put the ligands in alphabetical order. By the way, that is ignoring any type of prefix that you may have for those ligands. And what I mean by that is if I had a metal where there are at least 2 chlorines in there, I would say something like dichloral for that guy. And I would ignore the di part when I'm doing my alphabetical part of it. So we look at the C there rather than the D. By the way, that is how you would name something like chlorine that's there. It's chloral, kind of like what they do in organic. All the halogens, fluorine is fluoral, chloral, bromo, iodo for iodine. So that's sort of how those guys are named. If you have a name of a negative ligand that ends with the letter O, neutral ligands are usually called by the name of the molecule. There are a few exceptions. Water is known as aqua. Some books use aqua, A at the end. CO is carbonyl, NH3 is amine. Several ligands of a particular kind that's present. We do use, like I just mentioned, kind of the Greek prefixes, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6. If the actual ligand itself has already a prefix in it, one of those prefixes in it, then we roll to some other fun prefixes like bis for 2, tris for 3, tetrachus for 4, and so forth. So you may ask like bis for 2, 3, and 4. You may ask like, which one might that be? Like our good friend En. That is ethyl, endyl, diamine, basically. The di part of it's in the name. So because it already has the di in the name, you need to roll with one of these guys if you have multiples of those guys as well. Oxalate as well, even though oxalate doesn't really per se a prefix in it per se. People will sometimes also use the bis, tris, and tetrachus for oxalate if it's involved as well. The oxidation number of the metal is written in Roman numerals after the name of the metal. So remember that when you name the complex ion part, the metal part comes last in the name. And then after that, kind of like type 2 guys, you do use the Roman numeral to indicate the oxidation state on the actual metal. And that goes for things that we normally don't use Roman numerals on. So things like silver and zinc, where they have really fixed charges and we don't usually put the Roman numerals. We do typically will put the Roman numerals in this type of naming. In addition, as odd as it may sound, you could come across something that ends up being neutral, no charge, the metal. And you would actually put a Roman numeral, not really a Roman numeral, we put a 0 in the parentheses for that as well. So there are some weird ones where kind of the metal ends up being like neutral, 0 in terms of its oxidation state. And then we would also put that in sort of the Roman numeral spot. Now, if all these fun name things were not good enough here, if we have a negative complex ion, we will use not our regular metal name. We will roll it old school name and roll it with the 8. Like copper is cuprate, iron is ferrate, lead is plumate, and stuff like that. So you kind of roll it old school there if it is a negative complex ion part. If it's a positive one, then you use the regular name like iron, copper, whatever it may be. So if we go back to the ones we just left there, maybe. We take a look at this guy here. Actually, this guy here, we'll go to this one. So if we take our coordination compound there and we wanted to name it, we would start with the complex ion part in this case, which is positive. And there are 6 NH3s. So the prefix for 6 is hexa. The name for NH3 is amine. This would be a positive complex ion, which means we could just use the regular name for it, which would be chromium. A little Roman numeral 3 action happening there. Need a bigger screen here. And at that point, that takes care of all the complex ion part. By the way, if I just had the complex ion by itself, I would just put ion at the end of that, and that would be the name of it. But we do have our counter ion here, which is nitrate. And all counter ions are pretty much just use the name. Doesn't matter how many of them they are. So if it's nitrate there, we would use nitrate here. So the nice proper name of that guy that we have right here should be something like hexamine chromium 3 nitrate would be the proper name for that guy. Any questions on that one there? All right, so let's take a look at some of these ligands and some of the names that we do come across here. I think we got the tables coming up, so we'll take a look at those. So for example, here are some of the kind of neutral guys, some of the special names that go with it. Like I said, some people use aqua, some people use aqua for water. You could go either way. This is amine for NH3. That's methylamine, that's carbonyl, that's nitro. And like I said, here are sort of your halogens, your fluoral, your chloral, your bromo, your iodo. That's hydroxo, which is our hydroxide, and cyano for our cyanide as well. So if we had the one, which I think was this a second ago, right? 4, I think we got going on there, right? Oh, I got one more here before we get there. They might help us with this. Here are the ATE, our sort of older school way of naming these guys. So if your complex ion is negatively charged, you want to go with these names. So iron to be ferrate, cuprate, plumate, argentate, iurate, and stannate for tin. And again, if our complex ion is negative. So why don't you, now that we got that one up here, why don't you name this one and see what you come up with. Let's take a look. So from our previous work, we figured out that that guy there is +3. Also, just from the location of what we see, how it's arranged here, once again, this is going to be our complex ion. This would be our counter ion here. So just like in the formula of the name, we would start with the counter ion, and we simply would just use the whole name, which would be potassium here. And once again, if you happen to have had 2 potassiums or 3, you would still just call it potassium. You know, kind of the same way if you had something like this, K2O, that would be potassium oxide. So kind of the same idea that is there. Here we're going to go to our complex ion and start with our ligand, which we just have one in this case, type of ligand. And there are 4 of them. So the prefix for 4 is tetra. OH is our hydroxide, which now becomes hydroxo there. Now we can go with the metal here at the end of the complex ion part of the name. And we know that our complex ion is negative. So we will want to go with the older way of naming it, which would be iurate here. Lastly, we want to finish with some Roman numerals there. So potassium tetrahydroxyiurate 3. That is a mouthful, yes. Any questions on any part of that name there? Okay, fun with names. I like it. All right. Here's another table, again, of some other ones that maybe you might come across. So we see the hydroxo, oxo for oxide, carbonato, in case you're ordering that, nitro, oxalato. I feel like I'm at Starbucks here. I'll take a grande oxalato with a carbonato and 2 shots of oxo in there as well. We have carbonyl, we have our aqua, and here's the ethylenediamine, which is really the same, but most people, once again, in the name and format, will just use EN for that guy, and it's perfectly fine to do that. This is ethylenediamine. That's our EDTA guy here. This guy at the very bottom as well. All right. So why don't you try this one here, see what you come up with. Why don't you name it? Also, what is the coordination number on this guy as well? Okay, let's take a look. So figure out the charge maybe on the metal here. We do see that we have oxalate, which is -2. There's 3 of them, gives us a -6. We have 1 potassium, which is +1, and there's 3 of them, which does give you a +3. That means in this case, the chromium is going to be +3 as well to balance it out. Coordination number here would be, it would be 6. Again, oxalate is a bidentate one, which means for every oxalate, it will bind twice per molecule. And since there's 3 of them, you get basically 6 bonds in there, all from the single bonded oxygen in each of those cases. We also see that our complex ion here comes second, which means it is going to be negative. And obviously our counter ion here is positive. So we'll start with the counter ion, which is simply just going to be potassium. We will go with our ligand, which in this case is just the oxalate, and there's 3 of them. So this is trioxalato. And here we're going to go with chromate, as it is a negative, and Roman numeral 3 in that case. Yes. Any questions on that one? As I mentioned before, some people will very commonly use tris here, oxalato. So because it's a bidentate one, people will use that prefix as well. So you may see it written like that. Any question on those names there? Did your handout still have the water on it? Yeah. Well, how many waters did you have? It was a dot. It should have been dot. How many waters? 3 waters. Yeah. So just to tie all that together there, which was on there, C2O4. Write that real quick here. K3 CR C2043. So the only difference would be we would roll with the same name. When you have a dot in water, that makes it a hydrate, right? And there's 3 waters, so that you would just add at the end of this trihydrate, right? If you did have this one, which I think was what was on your handout there. Any questions on that there? Okay. Let's try a couple more here. Top one, let's do name. Bottom one, let's do formula for it. Table on your left, there are some more metal ATE names. Let's take a look, see how you're doing. So we'll start top one here. We see our complex ion part comes first, so it is positive. That means we could use the regular name there for our metal. Let's all figure out the charge there on the metal. So water obviously is neutral, and chloride here is -1. There's 2 of them, gives us a -2. Along with the chloride as our counter ion on the outside, also giving us a -1 charge. So obviously to balance all that out there, we are looking +3 in this particular case. Coordination number on this one would be, coordination number here would actually be 6. It's got 4 waters attached and 2 chlorides attached, or each monodentate. So coordination number here would be 6. So we're going to start with our ligands. So we have 4 of the waters. So that is like a tetra aqua or aqua, your choice. We have 2 of the chlorines, which would give us a dichloral. We do want to put these in alphabetical order, so which one should come first? Yeah, it should come this. We're comparing the A to the C here. So this would be tetra aqua dichloral. Now we're ready for the metal part of the complex ion, which we will just use chromium. We will use our Roman number, which is 3. And lastly, here we have our counter ion, which is basically chloride. And that would be chloride there. Tetra dichloral chromium 3 chloride. Any question on that name there? Again, if we didn't have the counter ion, it would be everything in front and you just put ion at the end of it. We're going to write the formula for this guy. So really we could just kind of put our parts together. We know that actually our complex ion here comes first because we do see the metal at the end of it. So that is the complex ion part. And then that would be our counter ion here. So starting with tris ethyl endyl diamine, that means tris is 3. So we basically got 3 of those guys, right? We have a cobalt, and that would make our complex ion part. Now we might want to figure out what our charge on our complex ion is, since En is neutral and this guy is 2, and we know that from the Roman numerals. The overall charge on the complex ion is +2. The reason that's important is now when I look at my counter ion, which is sulfate, I just need 1 of those, right, to balance it out. So that would give me a coordination compound that looks something like this. Any questions on that there? Okay, I'm gonna try a couple more here, I think. Let's go with names on these guys, see what you come up with. Yeah. Yeah. For the second one here, it would be, again, because this is bidentate and there's 3 of them. So the coordination number here would be 6, and it was 6 up on top as well. Yeah. Look, once again, I'm going to start with sort of identifying things. So we got our complex ion first, so it's positive. So once again, we can use the regular name on the metal. We have NH3, which is neutral. We have a Cl here, which is -1. And in this case, we have a couple of them on the outside there for our counter ion. Once again, giving us a +3. Not always going to be +3. It seems to be a lot of them popping out on these. So in this case, we do have 5 of the ammonia, which would give us pentamine. We also have 1 of the chlorals, and I think I actually threw it in alphabetical order there by not even looking. So that is A, and then that is C. So that would go in that order. Then we would use the regular name there. So putting this together would give us a penta. If I could write amine, chloral. We use the whole name there, which is cobalt, Roman numeral 3. And once again, even though there's 2 of them there, it's just going to be called chloride at the end there. Any question on that name there? Looking at our second one here, we got our potassium coming first and our complex ion coming second, which does mean our guy is going to be negative overall here. So we can start with just the counter ion, which would be potassium. Looking at our cyanide, which is -1, and there's 6 of them is -6. There's +3 on the outside from our potassium, and again, giving us our lucky number 3 there. This is going to be a hexacyano, right? And a ferrate in this case, because it's a negative complex ion. and a Roman numeral 3 at the end of it there. Any questions on that name there? And again, once again, if you had just the ion part here, by the way, the overall complex ion would have what type of charge this guy? Number writing? It is a -3, yeah. Again, why we have 3 of the potassiums there to balance it out. If you had this, pretty much you would just call it the hexacyanoferrate 3 ion. Yeah. So you just kind of put ion at the end of it if there's no counter ion present. Any question on that there? All right, 2 more to finish it out here. Let's do a couple more formulas. So write the formulas for each of these: triamine, bromo, platinum 2 chloride, and a little potassium hexafluorocobaltate 3. Sounds like fun. Yes. Okay, so let's take a look. So once again, I know this part up to here is my complex ion because it ends with the metal part of the name. That's always how it happens. That means obviously this is my counter ion there. So I can just kind of draw the parts and then put it together correctly. So triamine means I basically got 3 of the ammonias. Bromo means I got me a Br, and obviously I have a platinum. So kind of putting all that together, we got our PT, our NH3, and our BR. There you go. Again, to help us figure out, how many chlorides we might need, we need to kind of figure out what the overall charge is here. We know it's going to be positive. Once again, the NH3 is 0. This is -1. So overall, our platinum here is 2. Overall, we're looking at a +1 charge there for our complex ion. So that tells us that we really just need 1 of the chlorides there to balance it out. And that would give us our coordination compound that looks something like this. Any questions on that one there? Looking at the second one, we actually see the metal part of the name with an ATE at the end of it coming here second, which tells us this part is the complex ion. Also tells us that our complex ion is going to be negative in this case, with potassium being our counter ion. So hexafluoral is like an F6, and a CO would be cobalt, basically. Once again, we know the cobalt there from the name is +3. Obviously, our fluorine is -1, gives us a -6, which means overall here, we are rolling with a -3 on our complex ion. That's important because that means we need not 1, not 2, but we need 3 of those guys to balance it out. And that would give us something like K3COF6 right there. Yeah. Any questions on naming complex ions, coordination compounds, or writing the formula for any of those guys? Now, in the case here, top guy, the coordination number would be, if I wrote the actual number in there correctly, which I forgot on that side, that should be a 3. Coordination number on top guy is 4, yeah. So 3 of the NH3s there and 1 of the Br. And coordination number on the bottom guy there is 6, all of them coming from the fluorine. Yes. Yes. It refers to basically the complex ion part and the atoms from each ligand that are directly bound to the metal. So yeah, so we don't look at the counter ion for that. Just like we, when you're asked probably, what is the oxidation state of the metal, is usually referring to the complex ion part. Other questions? All right, then let's talk a little bit about isomers. Isomers are really the same sort of compound. Well, I should say that they are the 2 things or more things that have basically the same formula. But a lot of times isomers end up having different sort of connectivity, and that gives them some different properties, a lot of times different names. So they have the same formula, but some different properties. There's a couple of different types of isomers. There are structural isomers. which essentially have sort of different bonds that occur. And underneath that, there are coordination isomers and linkage isomers, which we'll look at in just a second here. There's also stereoisomers, which have the same bonds, but they're sort of arranged in three-dimensional space sort of differently. They're in sort of different locations. And that gives rise to geometric, which are cis or trans isomers, or optical isomers, which have the ability to sort of change the angle of polarized light. So let's take a look first at coordination isomers. So if we just count up everything that is there in the top guy and the bottom guy, and that SO4 actually should be up here, just kind of went down there. I think it's okay on your paper. We basically have one chromium in each. We got the 5 NH3s. We have one Br and one sulfate. The difference here between the top guy and the bottom guy is the sulfate here, right, is actually bound to the metal in the complex ion. And it is the bromine here that's acting as the counter ion here in this first instance. In the second instance, it is actually the bromine that is now being actually directly bound to the complex ion. And here the sulfate is acting as a counter ion in this case. So, and the first one, the sulfate is basically part of the complex ion. Second one, the bromine is part of the complex ion. Obviously, with some different things attached here, you would have some different properties. They're isomers again, because they basically have the exact same formula in each case. Now, linkage isomers are also isomers that basically have the same formula, but the difference is in the ligand, what it uses to bond to the complex ion or the ion or the metal ion that's in the middle. So if we look at nitrite, which is here, NO2 minus, in the top case, what is happening is it is the nitrogen and its lone pairs that are linking into the cobalt there. On the second one, it is still NO2 as the ligand, but it's attaching actually through the oxygen part of that particular ligand. So in this case, nitrite has an oxygen that's got some lone pairs that could actually donate, and it also has the nitrogen that can donate it. So it has the ability not to necessarily bind twice, but can bind with different actual atoms on the ligand. And that gives us our linkage isomers. Again, here, if we wrote the formula for all this, it would be sort of the same formula. It's just sort of the attachment point here in a linkage isomer that's different. Again, a different atom on the ligand there will attach. Question on that there. So let's talk a little bit about stereoisomers. Stereoisomers are sometimes also referred to as geometric isomers, and cis and trans isomers develop. Cis basically means like the same side, and trans means opposite sides. You come across cis and trans a lot in organic chemistry when you deal with double bonds, and you have groups that are on the same side of the double bond, and that's what's referred to as cis. Or you have groups that are on opposite sides of the double bond, which are known as trans. So when we talk about cis or trans here, we're mainly talking about sort of, are these guys in the same plane or sort of opposite planes, kind of one above the plane of the molecule and one below the plane of the molecule. So they have the same atoms and the same bonds, but different bond angles. They are common in square planar complexes. Square planar comes from octahedral, yes. Gives you that square in the same plane, right? And you got a couple of, non-bonding electrons happening out there as well. So if I go backwards, we go forwards. That's better. There you go. So here's again that sort of square planar, and A there is the cis isomer of this guy, and it has a yellow color, and B is the trans of this guy. And again, you can see it's the exact same formula. The difference is here, you can kind of see, you could pick either group in this case, but the ammonias, for example, are on the same side of sort of the plane. So are the chlorines, by the way. They are also on the same side, basically. We see here, though, on the bottom one, we have a chlorine kind of on the top edge there and a chlorine on the other side. So they're sort of opposite of each other in their locations, and that is what makes them trans in this particular case. And again, it will give them some different sort of properties if it's cis or trans. Here is a octahedral arrangement with a coordination number of 6. So this is more of octahedral, and A is trans. And in this particular case, all the ammonias here are sort of within the plane. And what we see here is the chlorine is one's kind of above the plane and one is below the plane. So sort of opposite sides of the central part of that compound there. And that would give you the trans. Here, this is the cis arrangement where, you know, they're sort of on the same side of the plane of the molecule, and that would make it cis in this particular case. And again, these guys would have some different properties based on sort of the location of those things. But once again, everybody is exactly the same in terms of what is present. It's just sort of their arrangement in three-dimensional space is a little bit different. So in more of a, what this is referred to as an octahedral sort of arrangement, you know, you kind of look above and below the plane of the center molecule to see if they're sort of on the same side or opposite sides. Question on that there. Now, optical isomers are isomers that have opposite effect on plane polarized light. The molecules have non-superimposable mirror images. They are what are referred to as being chiral, and the isomers are enantiomers. So a chiral compound, what it means is if you take a chiral compound and you put it up to a mirror, it will reflect back, right, an image. And if you take that image out of the mirror and you try to rotate it around as much as you want, you will never be able to get it to rotate in the correct orientation that you could then lay them both perfectly on top of each other where everything matches up. It's kind of like your hand. Yes, you put your hand up, you get your other hand staring at you. If you take the hand out of the mirror, you can rotate it around. Ow, that hurts. But you'll never be able to get everything correct, right? You go down, you got thumbs on the wrong side. You go this way, you got thumbs on the right side, but palm up, palm down, right? It doesn't perfectly match. So that's basically a chiral compound. If you pull out the mirror image, you could do as much rotation as you want. There's always going to be sort of a group that's just not going to line up perfectly in that situation. There are compounds which are known as achiral, where if you put it to the mirror and you take out the mirror image, you can rotate it perfectly to get them to sit exactly the same. And that usually involves where you got like a couple of groups that are the same. That sort of happens on that. So plane polarized light is obviously light that goes through a filter there. It gets separated out. And if you have your sample, it could rotate the light at a certain angle, which you can measure. And we're not going to do any of those type of calculations. So, but these type of guys have the ability to sort of rotate that light. There's your hand mirror type of thing. There we go. So here, if we look at these isomers here, isomer 1 and 2 are mirror images. That is, image 1 and 2 are identical to each other. They cannot be superimposed. So there's no way that you could rotate it that they will match. And it may be hard to see, but when we kind of do this into the mirror, it sort of reflects obviously back. And what ends up happening in that sort of reflection is this slight difference down here where in the original image, it is the nitrogen on the bottom that's connected right to the nitrogen right above it. In the mirror image, what ends up happening is this nitrogen actually gets connected to the back nitrogen. So when you pull it out, you're going to rotate it, but that nitrogen is always going to be in the wrong location and you won't be able to do it. So it's that slight different connection that sort of happens in the mirror image, which is here, where it gets connected to the back one versus just straight up connected right there to the front one. That causes the differences there in the mirror image and won't allow it to basically superimpose on each other. And again, if we look at these couple of things here, this is the trans isomer, which Again, when we reflect these guys back, we do actually preserve the sort of same connections, if you look over here, as what we had in our original one, which means when we pull it out, you will be able to just kind of rotate it around and it will fit perfectly. Once again, in our cis isomer here, when it reflects, we're going to get that different connection again between this nitrogen and this nitrogen now gets connected, and that's going to cause it to always be sort of in the wrong place. And the chlorine here will always be sort of in the wrong place as you rotate it around. It really won't match up really well. So when you do sort of reflect this, right, we kind of go reflects, this guy comes forward, this guy goes there, and again, this guy kind of goes to the back. So that's how we get those kind of odd connections that occur. So enantiomers are two molecules that have mirror images of each other that are non-superimposable. So the guy here on the right would be an enantiomer of each other. They're non-superimposable mirror images. A lot of biomolecules are chiral, and some drugs are also chiral, but only one of the isomers are effective in sort of curing a disease. Again, with those different sort of connections, you sometimes have some very different properties, even though they're sort of made up of exactly the same thing. Any questions on that there? All right, we will lay up the last part of this for next time.